Hello, good day everyone. We will continue our discussion in chapter 1 and we are now in uh, as you can see here we have chopping and rounding. So in this lecture we will for the rest of this discussion we will features uh, computer arithmetic, and also we will be focusing our attention to our familiar base 10 representation of numbers instead of base 2. Uh, Before that, as you can see here, we will introduce the normalized decimal floating point representation. This is the form. So remember, this is normalized decimal. So meaning to say decimal, it is in base 10. Okay, and with this representation we now know already that d sub 1 must not be equal to 0. So that's why if you can see in this inequality, d sub 1 will not take the value 0. So it will take numbers from 1 up to 9, and for I 2 to k, this is the range of the values since it is in base 10, and we call these numbers k-digit decimal machine numbers. So this is the definition for chopping and rounding. So your x here is a real number with more digits the computer can handle. So this means that there are, for example, in a calculator, if you can see your calculator, where's my calculator? Uh, yeah, see here. Uh, as you have noticed, this portion here is very small. The display is very small. So there are times when your display is small, uh, it will only display less digits than what is being expected. So if this calculator uses for example 32-bit representation, then it will only display up to, I guess, as you can see here, how many digits: 1 2 3 4 5 6 7 8 9 10 11 12. Okay, 12 digits only, okay, in the display sample here. Okay, so this definition basically means that if your display, for example in a laptop, it displays more digits than the calculator. So this is your x in floating point representation, d sub 1, 0 point d sub 1. So notice the fractional part, d sub 1, d sub 2 up to d sub k plus 1 dot dot dot. So this notation here, that 3 dots means this realm, your computer holds more digits. Okay, and the question is, how will the computer represent x? So we will use the notation FL of x, which represents the floating point representation of x. And for chopping and rounding, this is the definition. In chopping, we simply take the first k digits and ignore the rest. So meaning to say, if you look at the floating point representation of x, so it will chop. So the word chop is you cut. So from d1, d2 up to d sub k only. So this is what do we mean by chopping. Of course, you should not forget that times this expression here, times 10 to the n, you must also include it here. Okay, we will see that in the example later. For rounding, this is the same as in your uh, high school mathematics. If your d sub k plus 1 is greater than 5, then you have to add 1 to the previous digit that you are going to round. So to obtain the floating point representation of x. And if your d sub k is less than 5, meaning 1, 2, 3, 4, then you will do as in chopping. So for example, if you have here, find the 5 digit or significant digit, chopping and rounding values of the numbers. Letter A, your pi, and your B is this one here, 0.00123456 7. So we will solve this in the whiteboard later. Okay, let's have a comment here first before before I'm going to show you the solution. In letter A, in example 15, as you can see, um, this is the given is already in the floating point representation. Okay, and we know that pi is 3.1416 and so on and so forth. So in this given, it is already written in the floating point representation, if your x is pi. But however, in letter B, uh, it was not written yet in the floating point representation. So this uh, example, letter B, 15b, you should write it first in the floating point representation. And also there's a keyword here, it says 5 digit. It means that you are going to get the 5 significant digits. Okay, uh, let's go to the Google browser. I searched what do we mean by significant digits. This is the same as in your high school mathematics. You can open the Wikipedia. As you can see here, there are some rules to identify significant figures or digits in a number. So I know that you are very familiar with these rules. There's also this website here. You can type this URL in the Google browser. So for example here, this, if you have a decimal number, 0 before the what you call this number is not significant. If it is after the number, uh, it is always that uh, numbers numbers uh, non numbers like non-zero digits are significant, like 1 2 3 4 5 6 7 8 9 are all, these are all significant digits. This second rule, we have zeros between non-zero digits are significant. So these are the example. You just read this one and type this URL in the Google browser, then just to have a review. Okay, just to have a review. And also there's also a what do you call this one, let's make it let's zoom this one here, let's zoom it up to 133%. For example, there is a word here like this one, zeros between two significant non-zero digits are significant. So as you can see here, but there is a word here like resolution. This word, I don't know if you encountered this in your high school. It says here that 101.12003 has 8 significant figures if the resolution is 0.0001. Okay, So why? 1 to, so you consider how many, yeah, tens, 100,000s, 10,000, 100,000. So tens, 100,000. Okay, this is 100,000. Okay, so if this is less, like 0.001, this not less, if this is bigger, 0.01, then if the resolution is 0.01, then the significant digits will be less. Okay, so but usually if there's no word like resolution, then that will be the usual uh, way on how to identify significant figures in a number. So let's continue. Example 15, let's solve this example. How to get the 5-digit chopping and rounding of these numbers. So, okay, solution. This is for example 15. Okay, for letter A, our given is pi, which is equal to 0.31, sorry, 314159,265 times 10 to the 1. So these are the given is already in the floating point representation. So for chopping, uh, your answer is uh, FL of pi, uh, FL of pi is equal to, so k is 5, k is 5. So if you recall your our topic in your high school about significant digits, 0 here is not significant. So 1, 2, 3, 4, 5. Okay, so since we are going to find chopping, so the answer is 0.31415 times 10 to the 1. Okay, but if you look at the definition, it says here that uh, there's no the expression times 10 to the something, this one here, where are you, this one here, times 10 to the n is missing, but it is understood that you have to write the expression times 10 to the n. What will happen if you will not write it in uh, if you will not include 10 to the 1? So if this is missing, like let's say let's erase this one, then as you can see this will not be the correct value for pi, which is 3.14. The answer must be 3 point, say 3.14 15 9 9 to 65. So the answer would be this one here. Okay, round to no, chop up to k digit, 5 digit. Okay, so if we neglect or we will not write times 10 to the 1, then we will have a wrong answer. As you can see, this answer is the same as this one. Okay, they are just the same. For rounding, FL of pi is round to 5 digits, so the answer is 0.31416, okay, times 10 to the 1. As you have noticed, 9 is, okay, round to 5 decimal digits. So 9 is, as you can see in the definition, d sub k plus 1. K is greater than 5, so add 1. So this is the answer. For letter B, our given is 0.00, where are you? 1 2 3 4 5 6 7 1 2 3 4 5 6 7. So first is you have to write the given in the normalized decimal floating point representation. So this is equal to, let's have this color, 0.1234567 times 10 to the, you move 1 2 3 3, okay, positive 3. Okay, this is the normalized decimal floating point representation. So for chopping, FL of 0.0001234567, the answer is 0 point, this one here, 1 2 3 4 5. Okay, 1 2 3 4 5 times 10 to the 3. And for rounding, we have FL of 0.00123456 7. So the answer is 0.12346. Okay, this one here is greater than or equal to 5 times 10 to the 3. Okay, that's it for this topic. Okay, we will now move to this discussion. This topic, we have absolute error and relative error. Since computers only give approximations to real numbers, mostly, if we have a non-terminating decimal, like irrational numbers, that kind of numbers, we need to be clear on how we measure the error of approximation. So this is the definition of the absolute and relative error. So suppose your x asterisk is an approximation to x. So remember the notation for the approximation to the actual answer. The absolute error is defined as absolute value of x asterisk minus x, and the relative error is this expression x. We have the numerator is the absolute error divided by x. Of course, x is not equal to 0. So this is the definition of absolute and relative error. So let's have an example. Find absolute and relative errors of letter A. Let's say this one here. Let's open a new page. Example 17. Example 17, we have solution. for letter A. So our given is our x asterisk is 0.21 times 10 to the 1. Our x is 0.20 times 10 to the 1. Okay, solution. For the absolute error, error, sorry, for absolute error, we have absolute value of x asterisk minus x. Let's look at the formula. Okay, so our formula is correct. This is equal to x asterisk is 0.21. Sorry, this is 0.20. Our x is 0.20, right? 0.20. 0.20. Okay. So 0.21 times 10 to the 1 minus 0.20 times 10 to the 1. Okay. So what is 0.21? 0.21 minus our x is 0.20, sorry again, 0.20. Okay, so 0.21, I have here my calculator, 0.20. The answer is 0. Absolute value of 0.01 times 10 to the 1. Okay, am I right? Okay, so why is this? Just recall your, let's have a bubble thought here. Just recall your algebra. Okay, recall 0.21, your this expression here times 10 to the 1. 10 to the 1, as you have noticed, they are the same. 10 to the 1, 10 to the 1 is just like x. Okay, it's just like, imagine that it is just like x minus 0.20 x. Okay, so 0.21 minus 0.20 in your algebra, this is 0.01 x, and we know that our x is times 10 to the 1. 0.01 times 10 to the 1. Okay, so the operation is just to subtract these two and then copy the variable. Just imagine that this is just a variable, this one here. Okay, so after taking the absolute value, it is the absolute value of a positive number is positive. So this is 0. Sorry, this is 0.01 times 10 to the 1. So this is for the absolute error. For the relative error, so we have absolute value of x asterisk minus x over x. This is just the same as property of the absolute value. This one here, we know that our x is not equal to 0. So why did I did this? Because we already solved the absolute error and the numerator is the same as this one. So this is 0.01 times 10 to the 1. The denominator is 0.20, 0.2 or 20 times 10 to the 1 also. So we know that the rule of multiplication is just the same as this one here, numerical, is the same as in the division. So just imagine that your times this expression times 10 to the 1 and times 10 to the 1 is just a variable. Just imagine that it is just a variable. So what you will do here is just to copy. So you divide 0.01 divided by 0.2, 0.01 divided by 0.2 is 0.05, 0.05. Okay, times no, not times, but you can cancel out this one here. You can cancel out this one. The answer is 0.05. Imagine, if you recall, again, let's have a bubble thought here. Let's have a bubble thought somewhere here. Recall. So just imagine that in division, so imagine that times 10 to the 1 is just x, 0.20 times x. So in division, you can cancel out this one here. Okay, so the answer is 0.05. So this is the relative error, 0.05. Okay, so you can do the same for letter B and for letter C. So I will ask this in the puzzle. The answer, the absolute and the relative error for letter B and letter C in example number 17. So let's go now to this definition, definition 18. Okay, this is the definition of approximate. This is the definition of the significant digits. How to approximate your x star using s significant digits. So the number x star is said to approximate x to s significant digits or figures if s is the largest non-negative integer that will satisfy this inequality. Okay, so remember that this inequality is the relative error. So the upper bound is 5 times 10 to the s. So in this definition, you are going to find the value of s. So when, for example, let's have where are you? Where's the example? Let's have an example like, let's get the let's apply definition 18 to example 17a. Okay, so I will ask also the in the ed puzzle, what is the value of s for in applying definition 18 for example 17b and c. So we will try to solve example 17a. This is easy. Let's try to open a new page here. Okay, and solve my, so let's application of definition 18 to example 17, letter A. So notice that our given, we have x asterisk, which is 0.21 times 10 to the 1. Our x is 0.20 times 10. And as you recall, in your what do you call this, in the previous discussion, when we solve the relative error, this is the formula for the relative error. we know that this is 0.05. Okay, so we will try to find a bound. So this one here, 5 times 10 to the s 5, let's change the color. 5 times 10 to the s. So what should be our s? Our s here. Okay, so is it let's have a bubble thought here somewhere. Let's try s, like, is it 1, is it 2, is it 3, is it 4, is it 0? Okay, so let's try 0. It says here, if you recall, uh, it is the largest non-negative, so meaning non-negative integer. So s is equal to 0 is not included, so since it is not negative, right, so we will discard that one. Let's try s is equal to 1. Okay, s is equal to 1. So s is equal to 1, the result will be 5 times 10 to the 1, or I'm sorry, I think I made a mistake somewhere. This should be negative s. Okay, I'm sorry. So this should be negative s, negative s. Okay, to the negative 1 here. So let's replace that one. I didn't see it. Let's escape, go to our text studio, and then let's try to go to lemma. Where are you? Remark. This is, where are you? This one here. Definition 18. So we have 10 to the negative s. So this one here. Okay, so let's run and wait. Let's wait for a while. Okay, we are done. So let's go back. Where are you? Sorry, let's close this one first, and let's open this. 10 to the negative s. Okay, so what happened? Why does it doesn't change? That should be negative. Okay, sorry, this is negative s. Sorry, mistake again. So okay, so I think we're finished. So this is the correct definition. 10 to the negative s. Okay, so we have here 10 to the negative s. This one here is equal to what? 0 point, move 1, convert to decimal 1, 0.5. So we know that 0.5 is what they call this one, 0.5, am I correct? 5, sorry, 0.5, so that's correct. How about s is equal to 2? 5 times 10 to the negative 2, so that should be 0.05. Okay, so let's complete this one here. 5 times 10 to the negative 3 is 0.005. Okay, 5 times 10 to the negative 4 is 0.0005. Okay, which of these four numbers satisfies this inequality? Okay, as you can see here, this one fails. This one here. Again, we know that 0.005 is not greater than. So this 2 is the candidate. But if you look at the definition, it says that S is the largest non-negative. So between the two, 1 and 2, not negative 2, negative 3, but S, as you notice here, S is positive. But if you plug in this in the numerator, in the exponent, we have negative. Okay, but the question, the definition says that S is the largest non-negative integer, so it is non-negative, so it is positive. So meaning to say, between these two numbers, S is equal to 1 or S is equal to 2, the largest non-negative is S is equal to 2. So this is the largest, this one here. Okay, so therefore our S is equal to 2. Okay, our S is equal to 2, and then this one here. So this example, we say that therefore we say, let's put the conclusion. Therefore we say x asterisk, which is equal to 0.21 times 10 to the 1 approximates x, which is 0.20 times 10 to the 1 approximates to 2 significant digits, but not to 3 digits, but not to 3, but not to 4, but not to 1, but 2 significant digits. Okay, so this is the end of the solution. Okay, so let's go back to our slide. So it says here, when the computer approximates a real number x by the floating point, by its floating point representation, so what can we say about the error? Okay, so in this lemma it says that the relative error, which is this one, of approximating x by the floating point representation in k-digit normalized decimal floating point representation, satisfies this inequality. If chopping, we have 10 to the negative k plus 1, and if rounding, you have this formula here. So let's prove lemma 19 for chopping, and then let's leave to the viewers to prove the second assertion, that if you are going to use rounding, then this is the formula. This is the upper bound, 1/2 times the quantity 10 to the negative k plus 1. Okay, so let's try to prove lemma 19 in the case where we do chopping. Okay, so let's open now our open board. Let's have a new page here. So this is the proof of lemma 19. This is for chopping. Okay, this is for chopping. So we will give the proof for chopping, and the proof for rounding is similar, but it is tedious. So let x to be our x, which is this form, which is this form. Where are you? This one here. This is our x. Okay, so this is our x. So 0 point d sub 1, d sub 2, d sub k plus 1 times 10 to the n. Okay, so then what will happen if we use chopping? So we cut up to k digits. Okay, 0 point d sub 1, d sub 2, up to d sub k times 10 to the n. Okay, if chopping is used. Okay, so let's now plug into the formula. Okay, so our formula, as you can see here, where are you? Lemma 19. For the absolute error, this one here, let's copy this one. Observe that x minus fl of x, x minus fl of x. Maybe you are wondering, in the formula, let's go back of this one here. Notice that x asterisk is in the first what they call this one, not factor, but first term. Okay, your x here, the approximation is in the first term, while the what they call this one, the exact value is in the second term, and we write it as x minus x asterisk, which is very confusing. But remember, in your high school, let's move somewhere here, recall that x asterisk minus x is just the same as x minus x asterisk. Okay, they are just the same. Why? Because x asterisk can be written as negative of x minus x asterisk, and just just like in your high school, absolute value of AB is just the same as absolute value of A times absolute value of B. So we can factor, we can separate, we can use this property, this property here. We can write this as in this form, x minus x asterisk, okay? But absolute value of -1 is positive 1, so they are just the same, okay? So whether we write it as x minus x asterisk or x asterisk minus x, but since you are getting the absolute value, then they are just the same. Okay, well anyway, don't forget that we can write it in this form, x FL of x over absolute value of x. Okay, that's the same property as this one for division. The same rule for division. If you have absolute value of A over B, you can write as this one. They are just the same. So plug in, our x is our x is 0.d sub 1, d sub 2 up to d sub k plus 1 dot times 10 to the n minus, let's move it somewhere here, our FL of x is 0.d sub 1, d sub 2 up to d sub k times 10 to the n over absolute value of x, okay, over absolute value of x, 0.d sub 1, d sub 2, d sub k plus 1 times, I'm sorry, this is times 10 to the n, okay. Okay, let's have an illustration here. How do we subtract these two values here in the denominator? They are just the same, but it was chopped up to k. So notice that these numbers, d sub 1, d sub 2 up to d sub k, are the same numbers, right? It only matters here, this value here. So what if, let's have an illustration, let's have a bubble thought here. Somewhere in your mind, you imagine these things, okay? Like, let's have this color, let's say color red, color green. Example, if you have 0. This is our x, 0.1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the, let's say, 7 minus, we chop it up to, let's say our k is, let's say our k is 3, okay, k is equal to 3, okay. So our answer here is 0.123, right? Since we use chopping and our k is equal to 3, so 0.123 times 10 to the 7. So what would be the answer? Okay, so notice that if we subtract this one here, let's say this color blue, this first 3, okay. So the result would be 0.000, sorry, this one here, 0.00 I already discussed with you, why is it that you have to copy this expression 10 to the 7 here? Okay, this is because we are doing with subtraction or addition. Okay, so just recall, and then notice that since our answer must be, let's what I call this one, verify it first. Why is this correct? If we subtract 0.123456789 minus 0.123, so we are correct. Okay, so let's write our answer in normalized decimal floating point representation. So since our d sub 1 here, our new d sub 1 is what we call this one, our d sub 1 here, as you can see here, is 0, and we know that by definition d sub 1 must not be equal to 0. So we will write this one as 0.45678 times. So you move how many places? 1, 2, 3, 4. Sorry, not 4, 3. 1, 2, 3. This one here. Okay. So our answer will be 10 to the 4, right? 10 to the 4. 10 to the 4. Okay. And as you have noticed, this is just by writing 8, 9 times 10 to the 7 minus 3. And if you recall, this exponent here, especially this 3 here is our k. Okay, that's our k. So meaning to say, and also before I forgot, this is our d sub k, right? D sub k, and this is our d sub k plus 1. Our d sub k plus 1 is 4, d sub k plus 2 is 5, so meaning to say this will be 0. D sub k plus 1, d sub k plus 2, d sub k plus 3, dot dot dot, times 10 to the n minus k. Okay, we know our n is 7. Okay, our n is 7, as you can see here. Our n is 7, and our k is 3, this one here. Okay, so the answer for the numerator is in this form, and of course copy the denominator, d sub 1, d sub 2 up to d sub k, d sub k plus 1 times 10 to the n. Okay, and if you take the absolute value, okay, you are going to take the absolute value, so this is positive. Okay, so 0. D sub 1, no, not d sub 1, d sub k, d sub k plus 1, d sub k plus 2 times 10 to the n minus k, and in the denominator also d sub k plus 1 times 10 to the n. Okay, so let's now have the bound for the numerator and the bound for the denominator. Okay, also the bound for the numerator and the bound for the denominator. is it that we have to bound? Okay, ask yourself. We have two simple bounds for the numerator and denominator. So why is it that we have to bound? If you recall in our lemma, we have here the inequality less than or equal. Okay, so therefore, what is being asked in the lemma is to get the bound. Okay, so for the numerator, we know that our numerator can be bound as times 10 to the n minus k. This is less than 1. Okay, that's very clear. Okay, you can ask yourself, why is it less than 1? And for the denominator, we have 0 point d sub 1, d sub 2, d sub k. I'm sorry, not this one here, this one. Okay, forget the 10 minus 10 to the n minus k. This is less than 1. Why is it that is k plus 1 is less than 1? Why is it? Okay, so forget about 10 to the n minus k, because we can cancel out this 2 here. Okay, we can cancel out, just like in our previous discussion. This is just like a variable x. Okay, with the same base, so the exponent will be subtracted. So what is the bound for the fractional part? So we know that this is less than 1. And here, this one here is greater than 0 0.1. Okay, the latter is true. Why is it that this is true? Since the smallest b sub 1 can be is 1. So just imagine using these bounds in the equation, above, we get, just plug in, okay, absolute value of x minus the floating point representation of x is less than or equal. The numerator is 1, the denominator is 0 0.1. This is safe that we can write less than, although this is greater than 0.1, since this is very small, times 10 to the negative k. This is times 10 to the negative k. Why is it that it is negative k? As you have noticed here, these two, if you have a bubble thought here, we have n minus k is n minus k, no, not k, this is n. So n minus k minus n, so the remaining value is negative k. So this one here, and we know that point 1 divided by point 1 is 10. Okay, times 10 to the negative k, or this is equal to 10 to the negative k plus 1. Okay, you can use your calculator if you will not believe me. That one is this one here. Okay, so we are done with chopping. As you can see, 10 to the negative k plus 1. Okay, so for remark 20, for rounding, don't forget that this will be your problem set. Okay, I will put that in the it paso. For remark 20, Lima 19 easily transfers to base 2 floating point representation. This is the IEE E 64-bit floating point representation of X. So if we are using base 2, and for chopping, the bound for the relative error is 2 to the negative 52, and for rounding is 2 to the negative 53. So I will give this as I will think first, okay, as a problem set. Okay, for our next topic will be this for lecture about machine epsilon, and I guess we only left with maybe 2 to 3 topics. Okay, and then we are done with chapter 1. So we know we can now proceed to chapter 2. So thank you so much for listening, and I hope that you enjoy learning something from this subject. God bless everyone.